On the 8th of March 2014, at 0:41 Kuala Lumpur local time, a Malaysia Airlines Boeing 777-200ER took off from the Malaysian capital's international airport, bound for Beijing. The flight had a scheduled duration of 5 hours and 45 minutes. It was a route the airline operated regularly, without incidents, without a history of problems. The aircraft in question, registered as 9M MRO, had been in service since 2002, with an impeccable record, 53,471 flight hours and 7,526 takeoff and landing cycles behind it. The last maintenance inspection had been carried out just 2 weeks earlier, on February 23. Its last check of the pilot's oxygen system had taken place the day before the flight, on March 7, a routine procedure that revealed no anomalies. 10 years later, however, leaked documents revealed that the aircraft was supplied with supplemental fuel and additional oxygen for the crew just before takeoff, a detail that the authorities had not publicly disclosed and whose relevance to understanding what happened afterward has been the subject of debate. There were 239 people on board, 227 passengers and 12 crew members. Most of the passengers were Chinese citizens, but there were also nationals of the United States, Indonesia, France, Russia, Australia, and several other countries among them. A group of Chinese calligraphy artists was returning home after a cultural festival in Kuala Lumpur. 20 engineers from the American technology company Freescale Semiconductor, specializing in semiconductors for aerospace and defense applications, unknowingly shared the flight. Entire families were traveling, some of them with small children. Among the passengers was also a person who worked as a stunt double for actor Jet Li. Many families lost several members on a single flight. None of them knew that this flight would be their last. In command was Captain Zahari Ahmad Shah, 53 years old, one of Malaysia Airlines' most senior pilots. He had joined the company in 1981 as a cadet, accumulating more than 18,000 flight hours over the course of his 3-decade career. He was a respected pilot, known among his colleagues for his technical meticulousness and his fondness for his home flight simulator. His co-pilot was Farik Abdul Hamid, 27 years old, an enthusiastic first officer who was on his final supervised training flight before obtaining full certification on the Boeing 777, the same model that would take him on his first solo flights. The aircraft itself was one of the most reliable aircraft in modern commercial aviation. The Boeing 777-200ER, introduced in 1994, has an exceptional safety record. At the time of the disappearance of MH370, the only 2 serious incidents documented in the model's history were an emergency landing at Heathrow in 2008 due to ice crystals in the fuel, and an accident in San Francisco in 2013 caused by pilot error. The model had never suffered a catastrophic loss due to technical failure. The 2 Rolls-Royce Trent 892 engines that powered 9M MRO were equally known for their reliability. The aircraft was configured to carry 282 passengers in Malaysia Airlines standard layout, with fuel capacity for intercontinental flights, giving it a flight range far greater than the 5 hours and 45 minutes scheduled for the journey to Beijing. That fuel reserve, combined with the diversion toward the south, is what allowed the aircraft to continue flying for more than 6 additional hours after disappearing from radar. The climb proceeded with absolute normality. Communications with air traffic control were routine. There was nothing that drew the attention of operators on the ground during the initial 40 minutes of the flight. 40 minutes after takeoff, while flying over the navigation point known as Igari in the South China Sea, Captain Zahari spoke the flight's last recorded words, "Good night, Malaysian 370. It was the usual protocol greeting when leaving Malaysian airspace before connecting with Ho Chi Minh's Vietnamese control. The tone was calm, professional, completely ordinary. After that phrase, total silence. The aircraft never contacted the Vietnamese controllers. It did not reach Beijing, the Frest. It did not activate any emergency signal. It did not send any distress message. There was no mayday. It disappeared. In the following minutes, Vietnamese controllers attempted to establish contact without receiving a response. They alerted their Malaysian colleagues. They in turn attempted to contact the aircraft through different radio channels. Nothing. Malaysia Airlines began trying to locate the aircraft through the ACARS system, the automatic flight data reporting system that allows aircraft to transmit technical information about the engines, systems and navigation in almost real time. Nothing either. At 2:40, the time at which the flight should have landed in Beijing, the aircraft in distress protocol was activated. Flight MH370 had disappeared from the map. The initial response from Malaysia Airlines and the Malaysian government was clumsy and erratic. The airline took hours to notify the passengers' relatives, who had gone to Beijing airport to pick up their loved ones and found the flight marked as delayed, with no further information for agonizing hours. When news of the disappearance was publicly confirmed, the handling of communications generated additional confusion. The airline issued several contradictory updates within a matter of hours, and Malaysian Transport Minister Hishamuddin Hussein appeared before the media without clear information to offer. The Malaysian government stated for days that there was no reason to suspect terrorism while simultaneously investigating every possibility. The lack of coordination between the various Malaysian agencies and the delay in sharing military radar data turned the first days into a crisis management catastrophe that amplified the family's pain. Years later, that handling would be one of the factors that would fuel the cover-up theories surrounding the case, or so it seemed. What happened next in the immediate hours demonstrates the first major failure of the system. The aircraft had not disappeared from the sky. It had disappeared from civilian radar, but Malaysian military radar continued tracking it without anyone taking any operational action. The secondary surveillance radars used by civil aviation depend on the cooperation of the aircraft itself. The aircraft's transponder receives a signal from the radar and automatically responds by identifying the flight number, its altitude, and its speed. It is a system designed for the efficient management of air traffic, not for tracking aircraft that do not want to be tracked. When MH370's transponder was deactivated at 1:21 local time, the aircraft disappeared from civilian screens as though it had ceased to exist. But military radars are fundamentally different in their operating principle. They operate on a primary basis, emitting pulses of electromagnetic energy that bounce off any metallic object in the air, regardless of whether that object cooperates or not. And the Malaysian Armed Forces' primary radar continued seeing MH370 for almost another hour after it disappeared from civilian screens. What that radar recorded is extraordinary. The aircraft, instead of continuing northeast toward Beijing, turned sharply west, crossed the entire Malay Peninsula from east to west at normal cruising altitude and speed, flew over the Strait of Malacca and entered the Andaman Sea. The aircraft flew over inhabited areas, over coastal cities with thousands of residents, including Penang, the hometown of Captain Zahari Ahmad Shah himself. It flew with precision, with no signs of violent depressurization or an evident mechanical emergency situation. A perfectly functional aircraft moving deliberately in the opposite direction from its declared destination. And the Malaysian military did not report this to the civilian authorities until days later, when the search had already been mistakenly concentrated in the South China Sea. This delay in sharing information had direct and irreversible operational consequences. The critical first days of search and rescue were concentrated in the wrong area. Vessels and aircraft from multiple countries searched the South China Sea, the last position known to civilian radar, while MH370 had flown for hours in a completely opposite direction. The reasons why the Malaysian military took days to reveal that information have never been fully explained. When the data were finally shared, The search had to be reorganized from scratch, with hopes of finding survivors already practically extinguished. The British satellite company Inmarsat operates a global communications network that allows commercial aircraft to send and receive operational data through space. The system works through periodic signal exchanges between the aircraft and the satellite, even when the aircraft is not actively transmitting any text or data message. Approximately every hour, the satellite sends a check signal to the aircraft to verify that the connection remains available and the aircraft responds. These exchanges are called handshakes. MH370 had the ACARS system deactivated, but the handshake protocol operates at a lower technical level, completely automatically, independently of any crew decision regarding communications. During the hours following MH370's disappearance from radar, the Inmarsat satellite recorded 7 handshakes with the aircraft. The last of them occurred at 8:11 UTC, 7.5 hours after takeoff. That 7th and final ping was partial, incomplete, different from the previous ones in its technical parameters. Inmarsat engineers interpreted that anomaly as a sign that the aircraft was beginning a communications system restart process, a sequence that typically occurs when the engines are shutting down due to fuel exhaustion and the aircraft's electrical system enters emergency mode. The analysis of those 7 handshakes allowed something unprecedented in the history of aviation, partially reconstructing the trajectory of a completely silenced aircraft through pure signal mathematics. Each handshake recorded 2 critical parameters. The first was the BTO, burst timing offset, the exact round-trip time of the signal between the aircraft and the satellite. Since radio signals travel at the speed of light, travel time is directly proportional to distance. Plotting those distances as arcs over the Earth's surface, Inmarsat engineers generated the now famous 7th arc, a curve that crosses the southern hemisphere and somewhere along which the aircraft had to be located at the time of the final handshake. The second parameter was the BFO, burst frequency offset, which measures the frequency shift of the signal due to the Doppler effect. When the aircraft moves away from the satellite, the signal arrives at a slightly lower frequency. When it approaches, it arrives at a slightly higher frequency. This shift is measurable with sufficient precision to determine the aircraft's general direction of movement relative to the satellite. The BFO values recorded during MH370's handshakes were consistent with an aircraft moving south and not north, which allowed investigators to rule out the northern corridor of the 7th arc, which crossed Central Asia, and concentrate the search on the southern corridor over the southern Indian Ocean. This conclusion was publicly confirmed on the 24th of March 2014 by the Prime Minister of Malaysia, Najib Razak. Flight MH370 ended in the southern Indian Ocean. The analysis implied that the aircraft had flown for approximately 6 additional hours after disappearing from radar, until exhausting its fuel in a remote area without radar coverage or regular maritime coverage. There were no possible survivors. The announcement turned what until then had been a search and rescue operation into an accident investigation. The families who had spent weeks waiting for news received confirmation of what many feared but none wanted to assume. The Inmarsat analysis was itself an unprecedented technical achievement in the history of aviation. The company's engineers worked for days with the handshake data, using methods that had never before been applied in an aviation accident investigation. The methodology was reviewed by external experts from the British government and Australia's ATSB before being accepted as valid. The raw data were also provided to independent teams for verification. The technical consensus among the experts who reviewed the analysis was that the methodology was sound, although with margins of error that implied uncertainty about the exact point of impact. That uncertainty, expressed in terms of tens or even hundreds of kilometers along the arc, became the central problem of all subsequent searches. What no one could yet answer was why. From the very beginning, the investigation had to confront an uncomfortable question. MH370 systems did not stop functioning accidentally. They were deliberately and sequentially deactivated by someone with specific technical knowledge of the Boeing 777. The transponder was switched off at 1:21, just as the aircraft crossed the boundary between Malaysian and Vietnamese airspace at the exact moment when the crew should have contacted Ho Chi Minh Control. That precise instant was not a synchronization accident. It was the moment of least supervision, the transition point between two control centers. The interval during which an aircraft can go unnoticed for the longest possible time before someone notices that it has not established contact. ACARS had stopped sending reports even earlier, at 1:07. Although the controversy over whether it was actively deactivated or simply had no transmissions scheduled until later continues to be the subject of technical debate among experts. The route diversion and the return over the Malay Peninsula required the manual entry of new coordinates into the aircraft's flight management system, the FMS, something that does not happen accidentally. The sum of these actions led the Malaysian Prime Minister to declare from the first days that someone was trying to hide the position and course of the aircraft. Malaysia's official investigation, in a country where the political consequences of blaming one of its own citizens were evidently delicate, never went so far as to identify any specific person responsible. There is an additional technical detail that investigators have analysed in relation to the system deactivations. The sequence and the exact moment at which they occurred suggest that whoever carried them out waited for the instant of least operational visibility. The space between two air traffic control sectors, where the aircraft had ceased to be under the responsibility of the Malaysian sector and had not yet established contact with the Vietnamese sector, is the interval with the lowest probability that an alarm would be detected immediately. That precision in the chosen moment reinforces the hypothesis that the deactivations were premeditated and not the result of an improvised emergency. The initial investigations examined the passenger list meticulously. Two of them, both young Iranians, were travelling with stolen European passports, which triggered alarms about a possible terrorist attack. However, the lead turned out to be a dead end. The two young men, Puria Noor Muhammad Mirdad and Delavar Sayed Muhammad Reza, were simply seeking to emigrate to Europe irregularly, using documents acquired on the black market. They had no links to any known terrorist organization. No group claimed responsibility for the supposed attack. The hypothesis of external terrorism was ruled out by all the agencies involved. The focus then shifted toward the crew. The hypothesis of an aircraft hijacking was also analyzed and quickly ruled out. For a passenger or outside group to have taken control of the cockpit between the captain's last message and the change of course, they would have had to break into the cockpit in a matter of seconds, neutralize two pilots in their seats, and know the exact procedures for deactivating the transponder and reprogramming the FMS. All of that without anyone activating any alarm. It was technically possible, but statistically improbable to the point of being dismissible. Furthermore, no group claimed responsibility. The focus concentrated, inevitably, on Captain Zahari Ahmad Shah. Investigators searched his home in Kuala Lumpur and found something that set off all the alarms. A home flight simulator built by himself with specialized hardware, including multiple screens and cockpit controls. It was a relatively common practice among pilots with a strong aviation vocation and the resources to afford it, but the contents of the simulator files proved disturbing. The forensic analysis of the system, carried out by experts from the United States Department of Defense, made it possible to recover several files that had previously been deleted from the simulator's drives. Among those recovered files were 7 geographic coordinates that corresponded to a flight route ending in the southern Indian Ocean. Some of those coordinates matched actual airways in the southern Indian Ocean, suggesting a certain level of planning rather than a random navigation exercise. The official report warned that there was no conclusive evidence that those coordinates had been entered in a single session, or that they reflected a premeditated intention linked to the March 8 flight. A pilot passionate about advanced simulation has perfectly ordinary reasons to explore long and complex routes on his home simulator. However, the detail that the files had been deleted added a layer of ambiguity that investigators could not ignore. The first official reports described the captain as a quiet family man with no history of problems, but later journalistic investigations, particularly an extensive investigation published by The Atlantic magazine, documented aspects of his private life that did not fit that profile. His wife had left the family home days before the flight. He showed signs of social and emotional isolation. Posts on aviation forums and social networks showed a man who devoted increasingly more time to his simulators and less to social life. None of this is conclusive, and the formal investigation never found clear indications of diagnosed psychological problems. But the cumulative picture of circumstantial evidence points systematically in one direction. The hypothesis of pilot suicide with mass murder of the passengers, carried out through deliberate control of the aircraft until fuel exhaustion over the southern Indian Ocean, is for most independent investigators, and for many officials, the explanation most consistent with the totality of the available data. It implies that the captain depressurized the cabin to incapacitate the passengers and the co-pilot, disabled the communication systems to avoid being located, and flew into the void, fully aware of what he was doing. It is a hypothesis that the Malaysian government has never officially endorsed, with consequences that go beyond the technical. If confirmed, it would imply that Malaysia's flag carrier failed to detect a severe problem in one of its most experienced pilots. For more than a year after the disappearance, the silence was absolute. No debris, no physical clue. The underwater search in the southern Indian Ocean, led by Australia with the participation of China and Malaysia, found only darkness at a depth of 4,000 meters. Then, on the 29th of July 2015, a man named Johnny Begg was carrying out cleaning work on a beach on Réunion Island, a French overseas territory located in the western Indian Ocean about 700 kilometers east of Madagascar, when he found a metallic piece almost 2.5 meters long, covered with marine barnacles, partially deteriorated by prolonged exposure to salt water. It was a flaperon, the aerodynamic control surface located on the trailing edge of an aircraft wing used to increase drag and control descent. Technicians sent from Australia and France examined the piece. French experts identified it as belonging to a Boeing 777. The only Boeing 777 missing in the world was 9M MRO MH370. The flaperon was covered with barnacles of the species Lepus anatifera, marine organisms that only grow attached to surfaces submerged underwater. Scientists analyzed those barnacles in detail, their size, their distribution over the piece, and the growth layers in their shells provided information about how long the piece had been floating adrift. The presence of organisms of different sizes and stages of development was consistent with exposure to water for approximately 16 months, coinciding with the time elapsed since the aircraft's disappearance in March 2014. Analysis of ocean currents using drift models demonstrated that an object with the characteristics of the flaperon, with its specific shape and density, could have reached Réunion from the southern Indian Ocean in that period of time by following the Indian Ocean subtropical gyre, a large-scale circular current that dominates surface circulation in that basin. The flaperon was the first solid physical evidence that MH370 had crashed in the Indian Ocean. Its discovery changed the status of the case from missing to crashed, although the location of the crash was still unknown. That discovery inaugurated a new dimension of the investigation, the systematic tracking of African, island, and southern coastlines in search of more fragments carried by the currents. and the fragments continued arriving during the following years. In February 2016, independent investigator Blaine Gibson, who devoted years of his life and his own money to searching for MH370 debris on the shores of the Indian Ocean, found on a sandbank in the Bazaruto archipelago off the coast of Vilanculos in southern Mozambique, a metallic object with the inscription "No Step" on its surface. Australian experts identified it as almost certainly a panel from the horizontal stabilizer of 9M MRO, a structural part of the aircraft's tail. Gibson himself found more fragments in Tanzania, Madagascar, and other African coastlines in the following months and years. The pieces continued accumulating. Segments of a door and engine parts on beaches in Mauritius and South Africa, a section of the outer wing flap off the coast of Tanzania, pieces of wing in Mozambique, cabin and interior materials at different points along the eastern African coast. By October 2017, 20 pieces had been recovered and analysed. Of them, 18 were identified by investigators as very probably or with almost total certainty from MH370, and the other two as probably from the crashed aircraft. No human remains were found, no significant luggage appeared, no documents or recognisable personal objects appeared. The forensic analysis of the recovered pieces provided technical information of direct relevance regarding the final moments of the flight. The flap fragments recovered in Mozambique and Tanzania were in the retracted or neutral position, not extended. This position is aeronautically significant. In any deliberate landing or ditching maneuver, the pilot extends the flaps to reduce approach speed and increase lift, allowing for a more controlled descent at a lower speed. The absence of extension points to there having been no landing configuration before impact, that is, that the aircraft struck the water without any aerodynamic preparation for the maneuver, compatible with an uncontrolled descent, or with a situation in which no one was operating the controls in the final moments. The geographic distribution pattern of the debris throughout the western Indian Ocean also provided valuable oceanographic data. An international team of scientists from NOAA, the University of Miami, the University of Santiago de Compostela, and Australia's CSIRO published a study in the Journal of Operational Oceanography, analysing the possible pathways of the fragments from the crash site to the locations where they were. Found the drift simulations, using data from buoys of NOAA's Global Drifter Array and numerical models of ocean circulation, concluded that the most likely crash site was located in the southeastern Indian Ocean, south of 30 degrees south latitude. The discoveries in Mozambique, South Africa, Mauritius and Tanzania were statistically consistent with a point of origin in that area, confirming the general direction indicated by the Inmarsat analysis. Finding floating debris was a notable scientific achievement, but the true objective was to locate the aircraft's main fuselage, the black boxes, and above all the cockpit, where the records could answer the questions that satellite data cannot resolve with certainty. The problem was monumental. The area of the southern Indian Ocean where the analysis pointed to the impact site is more than 2,000 kilometres west of Perth, Australia, which means that any ship takes several days to arrive and several days to return, drastically reducing effective operating time. The depths of the seabed in that area range between 2,000 and 6,000 metres, depending on the geological formations, which include abyssal plains, volcanic mountain ranges, canyons of tectonic origin, and trenches of considerable complexity. Much of that seabed had not been mapped with sufficient precision before the search began, which made it necessary to carry out exhaustive bathymetric surveys, scanning the terrain with high-precision echo sounders, before search equipment itself could be deployed. Without those prior maps, the search vehicles could collide with unrecorded underwater structures, as in fact occurred on several occasions. The first underwater operation, coordinated by the Australian Transport Safety Bureau with support from the Dutch company Fugro, used towed vehicles with side-scan sonar at depths of up to 4,000 metres. On several occasions, the equipment became caught on volcanic underwater mountains. In one specific incident, the vehicle crashed into an unmapped underwater volcano, requiring operations to be suspended to assess the damage. Despite these obstacles, the operation searched more than 120,000 square kilometers of ocean floor between 2014 and 2017 in what became the most expensive underwater search in the history of aviation, with a total estimated investment of more than $160 million contributed by Australia, Malaysia and China. The Australian ATSB published in August 2017 an analysis of satellite images collected on the 23rd of March 2014, 2 weeks after the disappearance, which classified 12 objects in the ocean as probably man-made. That study identified the crash area with what investigators described as unprecedented precision and certainty, placing it at coordinates 35 degrees, 36 south, 92 degrees, 48 east, northeast of the main underwater search area already completed. It was a result that came too late to redirect the search, but that confirmed that the aircraft was in the Indian Ocean. In January 2017, the 3 governments involved formally suspended the search. Without the aircraft located, without the black boxes, without direct evidence of its final fate, the case remained officially unresolved. The families received the news with a mixture of despair and determination. Without the fuselage, without the black boxes, the truth remained inaccessible. The second opportunity came in 2018 through Ocean Infinity, a then relatively young Texas-based company specializing in robotic underwater exploration. Its proposal changed the terms of the problem in 2 dimensions, technological and contractual. The company would not charge the Malaysian government unless it found the aircraft, a scheme called no find, no fee, that transferred all financial risk to the contractor. The incentive was enormous, up to $90 million if they located the wreckage within the agreed period. The technological difference compared with previous searches was substantial. Instead of the single towed vehicle system that Fugro had used, Ocean Infinity deployed from its vessel, Seabed Constructor, a fleet of up to 8 autonomous underwater vehicles simultaneously. These AUVs are essentially sophisticated underwater drones. They navigate completely autonomously, following programmed routes, without a physical connection to the surface vessel, and can operate at depths of up to 6,000 meters for periods of 48 to 72 hours, before needing to return to the vessel to recharge power and download the collected data. Each AUV carries high-frequency side-scan sonar, a multi-beam echo sounder for bathymetric mapping, a sub-bottom profiler, high-definition cameras, and a magnetometer to detect metallic masses. In practical terms, the use of 8 simultaneous AUVs multiplied by up to 8 times the area of seabed that could be analyzed each day compared with previous methods. Independent investigator Victor Ianello, who collaborated with Ocean Infinity during the preparation of the mission, described the difference clearly. The previous search used a single sensor gliding about 100 meters above the seabed with no significant maneuvering capability. Ocean Infinity's system was equivalent to sending 8 different teams to work in parallel over the same terrain, with sufficient maneuverability to adapt to the most irregular topography of the ocean floor, including the slopes of the volcanic mountain ranges that had proved problematic for towed systems. Ocean Infinity searched new areas identified by the ATSB as having high statistical probability during the first months of 2018, covering more than 112,000 additional square kilometers of ocean floor. The result was the same as in the previous search: no anomaly compatible with the wreckage of a Boeing 777. The second search ended without finding the aircraft. However, the second operation was significant for other reasons that transcend the immediate result. It precisely mapped areas of the southern Indian Ocean seabed that had previously been practically unknown to science. The probability models for the location of the impact were updated with new data that ruled out areas previously considered highly probable. And AUV technology unequivocally demonstrated its operational superiority for this type of search at extreme depths, validating the approach for future attempts with even more advanced equipment. In December 2024, the Malaysian government announced what many families had requested for years: a third underwater search. The contract was signed again with Ocean Infinity under the same no find, no fee scheme, this time with maximum compensation of $70 million if the wreckage was found. The designated search area covered 15,000 square kilometers in the southern Indian Ocean, approximately between 1,900 and 2,000 kilometers west-southwest of Perth, aligned with Inmarsat's seventh arc, but in areas that previous attempts had not covered with sufficient resolution or that new statistical models indicated as having a higher probability. Operations began on the 25th of March, 2025 in a first phase, and resumed on the 31st of December, 2025 in a second phase, carried out by the vessel Armada 8605. This time, Ocean Infinity used Hugin 6000 AUVs from the Norwegian company Kongsberg, capable of reaching depths of 6,000 meters. The technological evolution compared with 2018 was considerable in several technical respects. The new vehicles integrated synthetic aperture sonar, a technology that generates images of the seabed with much higher spatial resolution than the conventional side-scan sonar used in the previous search. Synthetic aperture sonar combines multiple acoustic emissions to simulate a larger antenna, producing images of the seabed with centimeter-level detail that in 2018 simply were not possible from the usual scanning distance. The AUVs also carried high-sensitivity magnetometers capable of detecting magnetic field anomalies produced by metallic masses, even when those masses are partially covered by marine sediment. High-definition cameras and laser scanners made it possible to generate three-dimensional models of the terrain with a precision that would have been unthinkable in previous searches. Improved energy autonomy allowed each vehicle to operate continuously underwater for up to 100 hours. The fleet of drones operated in coordinated formation, following systematic lawnmower patterns over the areas of highest statistical probability. The data were downloaded to the mothership upon each surfacing and processed almost in real time by analysts on board, who could adjust subsequent search patterns based on previous findings. In the second phase, the AUVs specifically covered the so-called IG hotspot, an area centered on coordinates 34.23 south, 93.78 east, derived from oceanographic studies and signal analyses published in 2020 by independent research groups. Scanning that area with synthetic aperture, sonar and magnetometers produced no anomalous detections that could be correlated with the fuselage of a Boeing 777 or with its engines or main structures. In total, the two phases of the third search covered 7,571 square kilometers of seabed. Adverse weather conditions in the southern Indian Ocean during the austral summer interrupted operations on several occasions, limiting effective working time. In March 2026, exactly 12 years after the disappearance, the Malaysian Investigation Bureau confirmed that the search had produced no finding, confirming the location of the aircraft. The vessel Armada 8605 was reassigned to other work. The contract with Ocean Infinity formally extends until June 2026, but the probabilities of an immediate resumption are low due to the approach of the austral winter and the seasonal deterioration of marine conditions at those latitudes. To understand why finding MH370 is so extraordinarily difficult, even with cutting-edge technology, it is essential to understand the terrain where the search is being conducted and the physics of what occurred at the moment of impact. The southern Indian Ocean, at the latitudes where the Inmarsat analysis places the point of impact, is one of the most hostile environments on the planet. The so-called roaring 40s and furious 50s, the winds that dominate the latitudes of 40 and 50 degrees south without any continental landmass to interrupt them, generate persistently extreme weather conditions. Waves regularly exceed 10 meters in height. Low-pressure systems rotate at cyclone speeds. Research vessels cannot operate for weeks at a time during the most adverse seasons, reducing periods of effective work to very specific seasonal windows of the austral summer. The logistics of supplying and maintaining underwater vehicles under those conditions is itself a notable engineering challenge. The seabed in that area is a combination of abyssal plains at depths of 4,000 and 5,000 meters, interrupted by volcanic mountain ranges rising several thousand meters from the seabed, tectonic trenches, canyons of erosional or seismic origin, and basaltic formations that sunlight has never reached. Many of these structures had not been precisely mapped before the search began. The creation of high-resolution bathymetric maps was, paradoxically, one of the most significant scientific contributions of the search effort, even though the families of the victims could hardly find comfort in that fact. Bottom currents are also a factor to consider. At the abyssal depths of the southern Indian Ocean, flows of cold water of Antarctic origin, known as Antarctic bottom water, move slowly over the seabed. These flows can drag light objects across the sediment over time, especially in areas with slopes. The lighter fragments of the aircraft would have drifted on the surface, with surface currents, and dispersed over wide radii. The heavier fragments, such as the Rolls-Royce Trent 892 engines, weighing nearly 7,000 kilograms each, or the main sections of the fuselage, should have sunk more directly and remained close to the point of impact, although even these may have shifted if the seabed terrain has steep slopes. The physics of the impact itself adds further complexity. If the aircraft descended in an uncontrolled mode at high speed, as suggested both by the retracted position of the flaps and by the BFO values of the final handshake, the impact with the water surface would have been catastrophic. At speeds above 400 knots, water effectively acts as a solid surface. The disintegration of the structure would have been almost instantaneous, generating thousands of fragments of different sizes that would have dispersed over a considerable radius on the surface before sinking at different speeds, according to their density and shape. The debris field on the seabed could be distributed over an area of tens of square kilometers, with the densest objects relatively concentrated and the lighter ones widely dispersed. This contrasts with cases such as Air France 447, which crashed into the tropical Atlantic in 2009. In that accident, the aircraft descended with the engines still running and the pilots active although overwhelmed by the situation, resulting in an impact at a lower speed than MH370 and a relatively concentrated debris field. Even so, the wreckage of AF 447 took 2 years to be found. MH370, with 12 years on the seabed and a probably much wider dispersal pattern, represents a search challenge an order of magnitude greater. The 20 fragments recovered on the shores of the western Indian Ocean are, in the absence of the main fuselage, the only direct physical evidence of MH370's fate. And those fragments, although they confirm the general direction of the crash, contain technical data that do not fit perfectly with any of the explanatory hypotheses in a definitive way. The condition of the flaps in the retracted position is the most debated fact among experts. That position points against an attempted controlled ditching, but the interpretation has important nuances. If the aircraft descended without active crew, that is, if the occupants of the cockpit were incapacitated or dead before the final descent, the flaps would remain in the position in which they had been left the last time someone operated them, which during cruise flight would be the retracted position. This interpretation is compatible both with the hypothesis of deliberate action by the pilot in the final moments and with that of prior incapacitation of the entire crew. The hypothesis of catastrophic depressurization without deliberate intervention deserves detailed analysis. An explosive depressurization event at cruising altitude around the 35,000 feet at which MH370 was flying would deprive all occupants of usable oxygen, and the aircraft followed a programmed route or the last route entered into the FMS, communications, and the aircraft's apparently methodical behavior during the first hours of the flight. However, it does not satisfactorily explain the prior deactivation of the transponder and ACARS, actions that require specific and sequenced technical steps that do not occur as a consequence of sudden depressurization. A variant of this hypothesis, explored by some investigators, involves an electrical fire in the aircraft's electronics compartment located directly below the cockpit. A fire in that area could have generated a sequence of electrical disconnections that progressively disabled the communication systems, followed by smoke penetration, sequential deactivation of the systems before the diversion. The landing gear door found among the debris added another layer of controversial interpretation. According to the analysis of some experts who studied the condition of the piece, the landing gear may have been deployed in the final moments of the flight. Deployment of the scientific knowledge generated about areas of the planet that were practically unknown before 2014. The bathymetric surveys carried out to prepare the search operations mapped with unprecedented precision areas of the southern Indian Ocean that did not appear in any detailed scientific database. The seabed of that region contains geological structures of extraordinary complexity, chains of underwater mountains of volcanic origin, extinct volcanoes tens of kilometers in diameter at their base, canyons of tectonic origin that descend thousands of meters, and abyssal plains covered by layers of sediment accumulated over millions of years. The data collected during the Fugro and Ocean Infinity operations represent a significant contribution to physical oceanography, submarine geology, volcanology, and the study of bottom currents in the southern Indian Ocean. The debris drift models developed for the MH370 case also advanced the state-of-the-art in operational oceanography. The work of teams from NOAA, the University of Miami, Australia's CSIRO, and other institutions to reconstruct the probable trajectory of the fragments from their discovery locations generated methodologies that have direct application in maritime search and rescue operations, in tracking ocean pollution, and in studying the distribution of plastic waste in the world's oceans. The Inmarsat handshake data, for their part, established a technical and legal precedent regarding the use of satellite signals for a purpose not originally intended to reconstruct aircraft trajectories. The BFO analysis methodology was completely new in its application to MH370 and has generated a high-level technical debate that remains active among experts in satellite signals, flight mechanics, and Bayesian statistics. Some independent researchers question aspects of the BFO analysis that determined the preference for the southern corridor, arguing that the margins of error in the Doppler effect data could be greater than the official models assume, which would open the possibility that the northern corridor was not completely dismissible. The search for MH370 also directly drove the development of deep-water AUV technology. The operational demands of searching the southern Indian Ocean seabed at 6,000 meters under extreme weather conditions led Ocean Infinity and the manufacturers of its vehicles to improve energy autonomy, hull robustness, the precision of inertial navigation systems, and the data processing capacity of AUVs. These advances have applications in offshore oil exploration, maintenance of submarine cable infrastructure, oceanographic scientific research, and future aircraft search operations. Among the alternative hypotheses about the location of MH370, one has gained considerable attention in recent years in independent research circles: the analysis of the WSPR network, an acronym for Weak Signal Propagation Reporter, a global distributed amateur radio system that continuously records the behavior of low-power radio signals in the high-frequency band. The theory was developed mainly by independent researcher Richard Godfrey with the collaboration of other investigators of the case. The premise is that aircraft in flight potentially detectably disturb the propagation of HF radio signals by acting as reflectors in the ionosphere or by modifying propagation conditions along the path between the transmitter and receiver of a WSPR signal. The WSPR network, which has thousands of amateur radio stations distributed throughout the world, automatically records each received signal with its time, frequency, and signal level. By analyzing anomalies in those records from the 8th of March 2014, the researchers proposed an alternative trajectory for MH370 that differs at several key points from the official trajectory based on Inmarsat, and that places the impact point at coordinates different from the areas searched so far. This hypothesis is actively debated in the scientific and technical sphere. Official investigative agencies, including Australia's ATSB, have pointed out that the sensitivity of WSPR signals to the presence of commercial aircraft at cruising altitude has not been demonstrated or scientifically validated rigorously through controlled experiments. Godfrey's results have not undergone peer review in specialized scientific journals with the methodological guarantees that such a process entails. However, the idea has gained enough traction among independent investigators and within Ocean Infinity's own planning deliberations for the third search to be incorporated into the analysis of areas to be covered. The IG hotspot area covered in the second phase of the third search was derived partially from studies that integrated WSPR data with conventional Inmarsat analyses. The fact that Ocean Infinity searched that area without finding anything does not definitively invalidate the WSPR method, but it reduces the probability assigned to that specific area in the updated models. Over 12 years, the families of the 239 people aboard MH370 have waged a battle parallel to the technical search, facing a type of suffering for which there is no precedent in the history of commercial aviation. Loss without confirmation, the absence of bodies to bury, the impossibility of mourning with an object. The Voice 370 group, which represents relatives of some of the passengers and crew members, has been the most persistent voice in demanding that the searches continue and that the governments involved assume full responsibility for resolving the case. After the conclusion of the third search without results, the group issued a statement urging the Malaysian government to extend Ocean Infinity's contract or allow other companies with deep-water exploration capability to operate under similar no-find, no-fee schemes. The group's central argument is direct. The current contractual model involves no expenditure for the government if nothing is found, so there is no legitimate economic reason not to extend the searches. Some families, particularly those of the Chinese passengers who constituted the majority of the occupants, have pursued legal action in different jurisdictions for years. In December 2025, a Beijing court, the Chaoyang District People's Court, ruled that Malaysia Airlines had to compensate 8 passenger families with more than $410,000 per claimant, reaching total compensation of nearly $3.3 million. The ruling was upheld by the Beijing Higher People's Court on the 8th of December 2025. The legal significance of this judgment exceeds the financial amount. It establishes a legal precedent in China for other pending proceedings related to Flight MH370, creating a basis upon which other families can claim compensation. Malaysia Airlines had already paid initial compensation in the years immediately following the disappearance, but the definitive resolution of the legal responsibilities of the airline and the Malaysian government remains the subject of litigation in multiple jurisdictions. The fact that the cause of the accident has never been officially determined extraordinarily complicates the assignment of responsibility. More than 120,000 square kilometers of seabed scanned in the first search. More than 112,000 additional square kilometers in the second. Another 7,571 square kilometers in the third. In total, more than 240,000 square kilometers of one of the deepest and most remote oceans on the planet, examined with the most advanced underwater exploration technology available in each period, and the Boeing 777 was not in any of those places. But the ocean floor did return information. The bathymetric maps generated during the searches revealed that the area contains massive unmapped volcanic structures, mountain ranges rising thousands of meters from the seabed, and canyons deep enough to conceal an aircraft beneath layers of sediment accumulated over decades. The sonar systems of Ocean Infinity's AUVs recorded geological anomalies of scientific interest, volcanic formations active in geologically recent times, and evidence of historical seismic activity on the seabed. None of those anomalies turned out to be MH370. The systematic absence of results in areas of high statistical probability does not imply that the aircraft is not in the Indian Ocean. The Inmarsat data, the debris drift models, and the physical findings on African shores consistently coincide in pointing to that ocean basin. But it does mean that some of the fundamental assumptions about the final moments of the flight, the exact descent profile, the impact speed, the gliding or non-gliding of the final minutes, may be shifting the calculation of the impact point enough for all the searches to have operated in the correct region, but in the wrong position within that region. The physics of the seabed adds another variable that experts have begun to consider more seriously. The abyssal sediments of the southern Indian Ocean can be deep and relatively fluid in specific areas where the rain of organic and mineral particles has accumulated layers of mud tens of meters thick over millions of years. An aircraft that struck the water at high speed and sank in those areas could become partially buried under sediment within a matter of months or years, which would considerably reduce its acoustic signature detectable by sonar. Ocean Infinity's AUVs are equipped with sub-bottom profilers, systems capable of sending acoustic signals that penetrate the sediment and bounce off denser objects inside, but the effective penetration range of these systems is only a few meters. If the fuselage, or the black boxes, are buried at greater depth, current technology might not be able to detect them from the normal scanning altitude of the AUVs. It is known with high certainty, supported by satellite data, ocean drift analysis, and direct physical evidence, that the aircraft flew toward the southern Indian Ocean and crashed somewhere in that basin. The BFO analysis of Inmarsat's 7 handshakes, ocean circulation models calibrated with data from NOAA's Global Drifter Array, and the 20 physical fragments recovered on the shores of the western Indian Ocean all point in the same general direction. The impact point is in the open sea, at depths of between 2,000 and 6,000 meters, in an area thousands of kilometers from any inhabited land. It is known that the aircraft's communication systems were deliberately and sequentially deactivated, and that the aircraft executed a change of course that required specific manual intervention on the navigation systems. It has not been officially determined who carried out those actions or for what purpose. It is known that the recovered fragments indicate that the aircraft did not perform a controlled ditching. The flaps in the retracted position and the descent rate values inferred from the final handshake point to an impact without landing configuration. The exact point of impact is not known. The black boxes, neither the flight data recorder nor the cockpit voice recorder, have been found. Without those black boxes, direct access to information about the final moments of the flight, the actions of the pilots, and the condition of the technical systems remains blocked indefinitely. In the absence of results from the third search, experts have proposed several possibilities that require reconsideration. The first is that the aircraft performed a longer final glide than assumed in the models, shifting the impact point farther south or farther north of the seventh arc than the current searches have covered. The second is that the aircraft impacted in an area with underwater topography that facilitated burial beneath sediment at a greater depth than current technology can penetrate. The third is that the BFO analysis, which determined the preference for the southern corridor over the northern corridor, contains larger margins of error than assumed, and that the impact point could be in a different area within the seventh arc. The fourth is that the correct area has still not been searched, because it lies outside the area delimited by the official models. The MH370 case also had direct and tangible consequences for global aircraft tracking standards. Before 2014, it was technically possible, although unlikely, for a commercial aircraft to disappear for hours without transmitting any data about its position. The disappearance of MH370 brutally exposed that gap. In response, the International Civil Aviation Organization adopted new standards in 2018, requiring all commercial aircraft above a certain weight threshold to transmit their position at least every minute in emergency situations and at least every 15 minutes during normal operations. Satellite tracking technology for aviation has advanced significantly since 2014, with systems such as ADS-B over satellite now capable of tracking aircraft over the oceans with continuous coverage, something that did not exist in 2014, on routes over the Indian Ocean. If MH370 had flown in 2024 with current systems, its position would have been known in real time throughout the entire flight, regardless of whether someone deactivated the transponder. The technical legacy of MH370 is, among other things, having forced a profound reform of the surveillance systems of global commercial aviation. Malaysian authorities have stated that they are willing to consider new searches if credible evidence about the location of the aircraft is presented, a condition that the Voice 370 group considers unnecessary, given that the no find, no fee scheme represents no economic risk to the government. The debate over whether to continue searching, where and with what technology remains open among official agencies, independent investigators, and the families of the victims. The seventh arc is the mathematical curve that defines MH370's horizon of possibilities. It is an abstract line, calculated from the round-trip time of a radio signal between an aircraft and a satellite that crosses the southern Indian Ocean like a crescent, thousands of kilometers long. Somewhere on that curve, or in its immediate vicinity, the aircraft rests. 12 years of searching have ruled out extensive sections of that arc. More than 240,000 square kilometers explored, no result. But the arc is long, the ocean is deep, and the aircraft is relatively small compared with the space that remains to be explored. Each new analysis model, each update of the drift data, each new interpretation of the Inmarsat handshakes slightly refines the estimate of the most probable point. The difference between what the models say and what the drones find on the seabed remains the most disturbing fact of the case, that all that mathematics, all that technology, all that coordinated effort by multiple countries for more than a decade has failed to resolve the most basic question about MH370. The case also has a dimension that transcends the accident itself. MH370 demonstrated that in 2014 it was possible for a commercial aircraft with 239 people on board to deliberately or accidentally deviate from its route and fly for hours over the loneliest ocean on the planet without any automated surveillance system detecting it in real time. That possibility previously theoretical, was catastrophically demonstrated. The response of the aviation industry has been to accelerate the deployment of global satellite tracking systems that close that gap. But the question of what happened on that specific flight, with those specific 239 people aboard that specific aircraft, remains unanswered. The locating signal of the black boxes, the acoustic beacons designed to emit signals underwater for 30 days after an accident and thus facilitate the recovery of the recorders, went silent in April 2014. Today, those boxes lie on the ocean floor without emitting any detectable signal. The beacons of the AF-447 recorders were heard and allowed them to be located. Those of MH370 fell silent before any ship reached their approximate coordinates. This reality has driven proposals within the aviation industry to extend the duration of black box beacons from 30 to 90 days, and to supplement physical recording systems with continuous real-time transmission of flight data by satellite, so that even if the black boxes are never recovered, at least the critical data are available on servers on land. These proposals are at different stages of regulatory discussion at ICAO as a direct result of the MH370 case. The Rolls-Royce Trent 892 engines of 9M MRO, if they are where the models suggest, have spent 12 years in the darkness of the southern Indian Ocean, under pressures of hundreds of atmospheres, in the cold of abyssal waters, perhaps covered with sediment and with the organisms that colonize any solid surface in the ocean depths. The black boxes, designed to survive impacts of thousands of Gs and pressures at depths of up to 6,000 meters, contain the recordings of the last 2 hours of sounds in the cockpit and the last 25 hours of flight parameters. They are the only document that could definitively answer the question that hundreds of families have been asking for 12 years. They are intact somewhere on the floor of the Indian Ocean. Only the eyes of underwater drones have any chance of finding them, and for that, those drones have to be looking in the exact place. They still have not found it. And until that happens, the greatest mystery of modern commercial aviation remains exactly where it has been from the very beginning, on the dark floor of the southern Indian Ocean, guarded by water and silence and the pressure of kilometers of depth, waiting for someone to finally look in the right place.